It carries load along its axis, spins without a drop of oil, ignores magnetic fields, and shrugs off acids that would pit steel in hours. Set beside a conventional bearing, it looks almost ordinary, 3 washers and a ring of balls, until it keeps turning where the steel one seizes. A thrust ball bearing is built for one thing: load pushed along the shaft rather than across it. A shaft washer, a housing washer, and a cage of balls between them carry that axial force. Machining every part from zirconia turns an ordinary axial bearing into one that runs dry, stays non-magnetic, and holds its form in heat and chemical attack. What lets this bearing run without oil is the pairing of a hard, finely finished raceway and a low friction coefficient. Zirconia races in balls polished to a very smooth wear surface, so rolling resistance stays low even dry. The same dry running behavior that would burn out a steel bearing is normal service for a full ceramic one, which is why these are chosen where oil cannot be tolerated. Beyond low friction, 3 features widen where this bearing can serve. Zirconia is chemically inert to most acids and alkalis, with only hydrofluoric acid and hot concentrated sulfuric acid as notable exceptions, so it survives wet and aggressive media. It is fully non-magnetic and electrically insulating, unaffected by the fields that disturb steel. And it resists water and salt water well enough for fully submerged service. 2 more features matter at speed and in heat. Zirconia has a density near 6 grams per cubic centimeter, roughly 70% that of bearing steel, so each ball is lighter, and lighter balls generate less centrifugal load on the raceway as speed climbs. Its thermal expansion is close to that of steel, which keeps shaft and housing fits predictable through temperature swings, and its strength and hardness hold with little change up to around 600 degrees Celsius. A single feature does not explain why a brittle oxide survives the pounding of a loaded raceway. The answer is written into the crystal. At room temperature, the zirconia grains are held in a metastable tetragonal form. When a crack starts to open and its stress field reaches a grain, that grain flips to the monoclinic form and swells by about 4%. The expanding grains press on the crack faces and stop it before it can run. This mechanism gives ZrO₂ stabilized zirconia a fracture toughness of roughly 7 to 11 megapascal root meters, among the highest of any engineering ceramic, and several times that of most oxides. It is that toughness, paired with high hardness, that lets a ceramic ball roll under repeated contact stress without the surface indentation or rolling contact fatigue that eventually spalls a steel race. On the raceway, that combination decides service life. Hardness resists the wear and indentation of rolling contact, toughness keeps microcracks from linking into a spall. Under clean load, a full ceramic race does not suffer the fatigue spalling built into steel, so its rolling life can far exceed that of a steel bearing of the same size. Dimensions follow the same boundary size series the bearing industry standardized long ago, so a ceramic thrust bearing drops straight into a seat cut for a steel one. The 51100 and 51200 series are the common families. A 51102, for instance, measures 15 mm across the bore, 28 on the outside, and 9 tall. A 51204 runs 20, 40, and 14. Bore sizes reach from a few millimeters up to 150 and beyond. Where the design departs from the standard is in the cage and the configuration. The ball retainer is commonly PTFE or PEEK, with stainless steel an option on larger bores, and a full complement build with no cage carries higher load at lower speed. Thrust bearings come in single direction and double direction forms, and outside the standard series the bore, outer diameter, height, and ball count can each be machined to a drawing. The application that draws most on these features is the high-speed precision spindle, the rotating heart of machine tools, turbines, and gearboxes, where a thrust bearing holds axial position while the shaft spins at tens of thousands of revolutions a minute. In that role, the Zirconia thrust bearing offers several things at once. Runs without lubrication. Low mass at high speed. Stable fits in heat. Non-magnetic and insulating. And long fatigue-free life. A dry running race removes the lubrication system a high-speed spindle would otherwise need. Balls at 70% of steel's weight cut the centrifugal load that limits top speed, so the spindle can turn faster before the raceway is overloaded. Expansion close to steel keeps preload and clearance predictable as the spindle heats under work. The race carries no magnetic field and no current, and without steel's fatigue spalling, it holds precision through a long service life.